Ever feel a rumble beneath your feet and wonder what's really going on down there? Today, we're journeying to one of the most remote and restless places on Earth to meet a true giant, the Pavlof Volcano. Tucked away in the Alaskan Peninsula, this isn't just any mountain. It's one of the most active volcanoes in the United States, a colossal force of nature that's been shaping the landscape for thousands of years. So grab your gear because we're about to get up close and personal with the fiery heart of Alaska. Pavlof stands as a majestic, near-perfect cone, soaring over 8,262 feet into the sky. It's part of the Aleutian Arc, a chain of volcanoes stretching from Alaska to Russia, often called the Ring of Fire. This region is a hotbed of tectonic activity, where the Pacific Plate dives beneath the North American Plate. This process, called subduction, melts rock deep within the Earth, creating magma that fuels the volcanoes above. Pavlof is the poster child for this powerful geological dance, a constant reminder of the planet's immense power. What makes Pavlof so special, and a little intimidating, is its incredible frequency of eruptions. Since the late 1700s, it has erupted more than 40 times, making it a superstar in the world of volcanology. Unlike some volcanoes that sleep for centuries, Pavlof likes to keep everyone on their toes. Its eruptions are typically strombolian, meaning they produce short, explosive bursts of lava, ash, and gas. Think of it like a spectacular but dangerous natural fireworks show. These eruptions can send ash plumes thousands of feet into the air, creating a serious hazard for aircraft. In fact, this part of Alaska is a major highway for international flights, so scientists at the Alaska Volcano Observatory watch Pavlof like a hawk, 24/7. The name Pavlov is Russian for Paul, but its history goes back much further. The Unangax people, the indigenous inhabitants of the Aleutian Islands, have lived in the shadow of this volcano for millennia. They have a deep spiritual connection to the land and the powerful forces that shape it. Their oral traditions and stories contain invaluable knowledge about the volcano's behavior, passed down through generations. For them, Pavlof isn't just a geological feature. It's a living entity, a powerful being that commands respect and understanding. Their ancient wisdom often complements modern scientific findings, painting a much fuller picture of this dynamic giant. So, how do scientists keep an eye on such a remote and wild volcano? It's a high-tech operation. The Alaska Volcano Observatory, or AVO, uses a network of seismometers to detect the faintest ground tremors that signal moving magma. Satellite imagery allows them to spot thermal anomalies, hot spots on the volcano, surface, and track ash clouds in real time. Webcams provide visual confirmation of any activity, and GPS stations measure ground deformation, literally the swelling of the mountain as magma pushes up from below. It's like giving the volcano a regular health checkup, but instead of a stethoscope, they use state-of-the-art technology to listen to its heartbeat. Living near Pavlof is not for the faint of heart. The nearest communities, like Cold Bay and Sandpoint, are small, tight-knit towns where residents have a profound respect for the volcano's power. They are accustomed to the occasional ashfall, which can look like a light dusting of snow, but is actually tiny, sharp particles of rock and glass. It can disrupt daily life, contaminate water supplies, and cause breathing problems. But these communities are resilient. They have emergency plans in place and work closely with scientists to stay informed and safe. It's a unique way of life, coexisting with one of nature's most formidable forces. One of Pavlof's most fascinating features is its relationship with its sister volcano, Pavlof's sister. This smaller, adjacent cone is a geological sibling, and together they form a striking dual peak. While Pavlof is constantly active, Pavlov's sister has been quiet for a very long time. Scientists are still studying the complex plumbing system beneath them to understand why one is so restless while the other slumbers. It is a geological mystery that highlights just how much we still have to learn about the inner workings of our planet. Are they fed by the same magma chamber? Or are their underground systems completely separate? The answers are still buried deep within the Earth. Let's talk about a recent major event. In March 2016, Pavlof roared back to life with one of its most significant eruptions in recent memory. It began with little warning, quickly escalating into a powerful event that sent an ash cloud soaring to 37,000 feet. That's cruising altitude for most commercial jets. The eruption was so intense that lava fountains shot from the summit, and lightning crackled within the dense ash plume, a phenomenon known as volcanic lightning. Airlines had to reroute dozens of flights to avoid the dangerous cloud. This event was a stark reminder of Pavlov's potential to impact not just the local area, but global travel and commerce. It was a textbook case for the AVO, whose rapid alerts and constant monitoring were crucial in preventing a potential disaster. The ecosystem around Pavlov is as dramatic as the volcano itself. The harsh, windswept landscape is home to incredibly hardy plants and animals. You'll find brown bears, caribou, and foxes navigating the volcanic terrain. The nutrient-rich ash from past eruptions has, over time, created fertile soils in some areas, supporting lush vegetation. The rivers flowing from the volcano's slopes are teeming with salmon, a vital resource for both wildlife and the local human population. It's a powerful example of how life not only survives but thrives in the shadow of destruction. Nature's ability to adapt and regenerate in such an extreme environment is truly awe-inspiring. As we wrap up our journey to the fiery giant of Alaska, it's clear that Pavlov is more than just a mountain of rock and fire. It's a dynamic, living system that shapes the land, the sky, and the lives of those around it. It's a natural laboratory for scientists, a sacred figure for the Unangaks people, and a constant, powerful reminder of the untamable forces that lie just beneath the surface of our world. Studying volcanoes like Pavlov isn't just about predicting the next eruption. It's about understanding our planet on the most fundamental level. It's about respecting the power of nature and learning to coexist with it. Thank you so much for joining me on this incredible adventure to the top of the world. If you are fascinated by the power of Pavlov, make sure to hit that like button and subscribe for more explorations into our amazing planet. Let me know in the comments which natural wonder you'd like to see next. Until then, stay curious. To understand why Pavlov erupts with such regularity requires a journey into the fundamental architecture of our planet to the boundaries, where massive plates of the Earth's lithosphere collide and grind against one another in a process that has shaped continents and destroyed civilizations. The Alaska Peninsula sits atop one of the most geologically active zones on Earth, where the Pacific Plate descends beneath the North American Plate in a subduction zone that stretches for thousands of miles along the Aleutian Arc. This is where the planet reveals its molten heart, where solid rock becomes fluid and rises toward the surface, carrying the heat of depths we can never directly observe. The Pacific Plate, one of the largest tectonic plates on Earth, covers much of the ocean floor beneath the Pacific Ocean. Formed at mid-ocean ridges where new crust continuously emerges from the mantle, this plate moves northwest at approximately 2 inches per year, a pace that seemed glacial until one multiplies it across millions of years. When oceanic crust meets continental crust, density determines the outcome. Oceanic plates, composed primarily of basalt and other dense minerals, are heavier than the lighter granitic rocks of continental crust. The denser plate must yield, bending downward and sliding beneath its continental neighbor in a descent that will eventually return it to the mantle from which it originally came. This subduction process generates earthquakes along the interface where the two plates meet, as friction resists the downward slide and then releases in sudden jolts. The Great Alaska Earthquake of 1964, one of the most powerful ever recorded at magnitude 9.2, resulted from exactly this mechanism, when a vast section of the Pacific Plate suddenly lurched deeper beneath Alaska, lifting the coastline and sending tsunamis across the Pacific Ocean. But subduction zones produce more than earthquakes. They are volcanic factories, and the Aleutian Arc represents one of the most productive volcanic chains on the planet. As the Pacific Plate descends into the mantle, it carries with it not just rock but water, trapped in sediments and bound within minerals that formed on the ocean floor. Water becomes crucial to what happens next. At depths between 60 and 100 miles, the increasing temperature and pressure cause chemical changes in the minerals of the descending slab. Hydrated minerals like serpentine and chlorite break down, releasing their bound water into the surrounding mantle rock above the subducting plate. This released water acts as a flux, lowering the melting point of the mantle rock from temperatures above 2,000 degrees Fahrenheit to temperatures that exist at these depths, around 1,800 degrees. The mantle rock begins to melt, not completely but partially, with the minerals that have the lowest melting points liquefying first. This partial melting produces magma that is more silica-rich than the mantle rock itself, because silica-rich minerals melt at lower temperatures than iron and magnesium-rich minerals. The magma, being less dense than the solid rock surrounding it, becomes buoyant. It begins to rise through fractures and weaknesses in the overlying crust, accumulating in chambers and reservoirs at various depths. Some magma crystallizes before reaching the surface, cooling slowly to form plutons of granite deep underground. But some continues its ascent, eventually breaking through to create volcanoes like Pavlof. The magma that feeds Pavlof is classified as andesitic, named after the Andes Mountains where this type of volcanic rock is common. Andesitic magma occupies a middle ground in the spectrum of volcanic compositions. It contains more silica than the fluid basaltic magmas that erupt from Hawaii's volcanoes, making it more viscous and prone to explosive eruptions. However, it contains less silica than the extremely thick rhyolitic magmas that produced the catastrophic eruption of Mount St. Helens in 1980. This intermediate chemistry gives Pavlof its characteristic behavior: frequent eruptions that are vigorous and ash-producing but rarely apocalyptic. The journey of magma from its birthplace in the mantle to the surface takes time measured in years or decades, not days. As magma rises, it may stall in crustal reservoirs where it cools, crystallizes, and mixes with surrounding rock or older magma from previous intrusions. The magma chamber beneath Pavlov likely resides at depths of several miles beneath the summit, a zone where molten rock accumulates under tremendous pressure, heated to temperatures exceeding 1,500 degrees Fahrenheit. Gases dissolved in the magma under this pressure include water vapor, carbon dioxide, and sulfur compounds. These gases remain dissolved as long as the pressure stays high, much like carbon dioxide stays dissolved in a sealed bottle of soda. When magma begins its final ascent toward an eruption, the decreasing pressure allows these dissolved gases to come out of solution, forming bubbles that expand and increase the magma's buoyancy. This degassing process accelerates the magma's rise and can lead to explosive eruptions. If the gas content is high, and the magma viscous enough to trap the expanding gases. In Pavlov's case, the eruption style typically involves strombolian to volcanian explosions, characterized by rhythmic blasts that hurl incandescent lava fragments into the air and generate ash plumes that can reach the stratosphere. The explosions occur as gas bubbles burst through the surface of the magma column, fragmenting the molten rock into ash particles that range from fine dust to blocks the size of automobiles. Understanding these processes allows scientists to interpret the signals that volcanoes send before erupting. The earthquakes detected by seismometers represent the fracturing of rock as magma forces its way upward. The ground deformation measured by GPS represents the inflation of the volcanic edifice as the magma chamber fills. The increased heat and gas emissions detected by satellites represent the approach of magma to shallow depths where its presence affects the surface environment. Each signal provides a piece of the puzzle, and together they allow volcanologists to assess the likelihood and potential intensity of an impending eruption. The escalation on March 27, 2016, the instruments monitoring Pavlov registered a significant change in the volcano's behavior. The seismic tremor, which had been episodic and relatively weak throughout the preceding weeks, intensified and became continuous. This sustained tremor indicated that magma was no longer simply accumulating in a deep reservoir, but was actively moving through the conduit system beneath the volcano, rising toward the summit crater. The character of the seismic signal shifted from discrete earthquakes to a continuous vibration, the signature of fluid movement underground, as if the mountain had found its voice and begun to hum with gathering energy. Scientists at the Alaska Volcano Observatory recognized this transition immediately. Continuous tremor represents one of the most reliable indicators that an eruption is imminent, typically preceding the surface breakout of magma by hours rather than days. The data showed tremor amplitudes increasing throughout the morning, and satellite imagery revealed a stronger thermal anomaly at the summit, indicating that magma had reached very shallow depths where its heat could directly warm the crater floor. By midday, the decision was made to elevate Pavlov's aviation color code from yellow to orange, signaling that the volcano was exhibiting heightened unrest with increased likelihood of eruption. The National Weather Service issued aviation warnings, and pilots flying routes across the North Pacific received notifications that Pavlov was showing signs of imminent activity. Commercial aviation treats volcanic ash as one of the most serious natural hazards because jet engines cannot tolerate the ingestion of ash particles. The fine glass-like shards of pulverized rock can melt in the high temperatures of a jet turbine and then solidify on cooler components, potentially causing engine failure. Several incidents in aviation history, including a British Airways flight that lost all 4 engines after flying through an ash cloud from Mount Galunggung in Indonesia in 1982 have established volcanic ash as a threat that demands absolute respect. In Cold Bay, the notification reached residents through various channels. Some received automated alerts on their phones, while others heard the news through the local radio station that serves as the primary communication link for remote communities across the Alaska Peninsula. The town's emergency coordinator reviewed protocols with key personnel, ensuring that shelters were identified and supplies of dust masks were available. The primary concern was ashfall, which could contaminate water supplies, damage equipment, and create respiratory hazards. The community had weathered Pavlof eruptions before, and the preparations followed established patterns born of experience. By late afternoon on March 27th, observers in Cold Bay could see changes at the summit through breaks in the cloud cover that typically shrouds the Alaska Peninsula. A dark plume rose from Pavlov's crater, initially modest in height but growing steadily as the hours passed. This was no longer just increased steaming but actual volcanic ash being expelled from the vent, the first visible confirmation that magma had reached the surface. The plume climbed to 10,000 feet, then 15,000, darkening as the eruption intensity increased. Lightning flickered within the ash column, a phenomenon caused by the friction between ash particles, generating static electricity that discharged in spectacular bolts illuminating the volcanic cloud from within. The eruption entered its explosive phase after sunset. In the darkness, observers witnessed incandescent lava fountains arcing above the summit crater, painting the ash plume with an orange glow that reflected off the low clouds. The Strombolian explosions, named after Stromboli Volcano in Italy, which exhibits similar behavior, hurled molten rock hundreds of feet into the air. Some of these lava fragments cooled enough during their ballistic flight to land as solid bombs on the upper slopes, while others remained partially molten and coalesced into lava flows that began descending the mountain's flanks. The flows were not massive rivers of molten rock, but rather narrow streams confined to channels in the volcanic cone, glowing serpents visible for miles against the dark landscape. Seismic monitoring revealed that the tremor amplitude had increased dramatically, indicating that large volumes of magma were now moving through the volcanic system. The explosions occurred in rhythmic sequences, each blast recorded by seismometers as a distinct signal superimposed on the background tremor. Infrasound sensors, which detect low-frequency sound waves below the range of human hearing, captured the acoustic energy of the explosions, allowing scientists to estimate the violence of each blast based on the pressure waves it generated. These explosions were expelling ash at velocities of hundreds of miles per hour, fragmenting the magma into particles ranging from microscopic shards to pebble-sized lapilli. The Alaska Volcano Observatory elevated Pavlov's status to red, indicating that an eruption was in progress and posed a significant threat to aviation. The ash plume, now reaching 20,000 feet and climbing higher, entered airspace used by international flights crossing between North America and Asia. Air traffic controllers began rerouting flights, adding hours to journey times but ensuring that no aircraft would encounter the ash cloud. The Volcanic Ash Advisory Center in Anchorage issued bulletins every few hours, tracking the plume's movement based on satellite imagery and wind forecasts. The ash drifted northeast, carried by prevailing winds that would eventually disperse it across hundreds of miles of Alaskan wilderness. Through the night of March 27th and into the morning of March 28th, the eruption continued with unrelenting energy. Ash fell on Cold Bay, a light dusting at first but accumulating as the hours passed. Residents woke to find their vehicles and buildings coated in gray powder, a reminder that they lived in a landscape where the Earth's internal forces could manifest with little warning. The ash was gritty, smelling faintly of sulfur, and it irritated eyes and throats when disturbed by wind. Those who ventured outside wore masks and goggles, and the town took on an eerie, muted quality as the ashfall dampened sound and reduced visibility. The eruption had transitioned from a possibility to a reality, and the mountain that had been merely restless was now fully awake. Yet this was only the beginning. Pavlov's eruptions typically lasted days to weeks, and the intensity could wax and wane unpredictably. Scientists monitoring the data knew that the volcano might sustain this level of activity or escalate further, potentially producing larger explosions and higher ash plumes. All they could do was watch, record, and relay information to those whose lives and livelihoods depended on understanding what the mountain would do next. The peak of fury. The eruption reached its maximum intensity on the evening of March 28th, approximately 36 hours after the initial explosive phase began. Seismic data showed tremor amplitudes spiking to levels that indicated extremely vigorous magma discharge, and the ash plume surged upward with renewed force, punching through the troposphere to reach altitudes exceeding 37,000 feet. At this height, the volcanic cloud entered the jet stream, where winds traveling at speeds over 100 miles per hour would carry ash across vast distances, potentially affecting air traffic as far away as the Canadian interior and the northern continental United States. Satellite imagery captured the plume's expansion in remarkable detail. Instruments aboard weather and Earth observation satellites detected the ash cloud's infrared signature, distinguishing it from meteorological clouds by its temperature and particle composition. The plume spread in a classic umbrella shape at the level where its buoyancy equaled the density of the surrounding atmosphere, creating a canopy of ash that stretched over 200 miles downwind from the volcano. Within this cloud, ash particles ranged from coarse fragments that would fall out within hours to microscopic shards of volcanic glass that could remain suspended in the atmosphere for days, traveling thousands of miles before finally settling to Earth. The explosions driving this ash production occurred in rapid succession, sometimes separated by only minutes. Each blast represented the catastrophic fragmentation of magma, as dissolved gases expanded explosively upon reaching the low-pressure environment at the surface. The violence of these explosions depended on the gas content of the magma and the rate at which pressure decreased during ascent. When gas-rich magma rose quickly through the conduit, the result was volcanic explosions that shattered the magma into fine ash and propelled it skyward at supersonic velocities. The sound of these explosions carried for dozens of miles, reaching Cold Bay as deep rumbles that rattled windows and reminded residents of the raw power being unleashed just beyond the horizon. Lava fountaining intensified during the peak phase, with incandescent jets of molten rock reaching heights of over 1,000 feet above the crater rim. This Hawaiian-style activity, somewhat unusual for Pavlov, given its typically more explosive behavior, indicated that portions of the erupting magma had lower gas content or that degassing was occurring more efficiently, allowing the magma to erupt as coherent liquid rather than fragmenting entirely into ash. The lava fountains fed flows that streamed down multiple flanks of the volcano, their paths determined by topography and the accumulated layers from previous eruptions. These flows traveled at speeds of several miles per hour on steep slopes, slowing as they descended and the lava cooled and thickened. Thermal imagery from satellites revealed the extraordinary heat being released. The lava flows appeared as bright streaks against the cold background of snow-covered slopes, their surface temperatures exceeding 1,800 degrees Fahrenheit. The heat flux from the eruption was sufficient to melt significant volumes of snow and ice on the upper mountain, generating meltwater that mixed with ash to create lahars, volcanic mudflows that pose their own hazard. These lahars, though not large enough to threaten distant communities, carved new channels down the volcano's flanks and deposited layers of ash-laden sediment in valleys below, adding another chapter to the geological record that future scientists would one day study. The atmospheric effects of the eruption extended beyond the immediate ash plume. Sulfur dioxide gas, released in large quantities during the explosive phase, reacted with water vapor in the atmosphere to form sulfuric acid aerosols. These aerosols, much finer than ash particles, could persist in the stratosphere for months, potentially affecting climate by reflecting incoming solar radiation. While Pavlov's eruption was far too small to produce global climate effects like the massive eruptions of Tambora in 1815 or Pinatubo in 1991, the sulfur dioxide emissions were measurable by satellite instruments and contributed to local air quality degradation downwind from the volcano. In Cold Bay, the ashfall intensified as the plume overhead thickened. Accumulations reached several millimeters in some areas, coating everything in a uniform gray blanket. The fine particles infiltrated buildings through any opening, covering surfaces and creating a pervasive dust that was impossible to exclude completely. Residents learned to keep windows sealed and to minimize outdoor activity, understanding that inhaling volcanic ash could cause respiratory problems ranging from irritation to more serious complications for those with pre-existing conditions. The town's water system required monitoring to ensure that ash contamination did not render the supply unusable, and equipment operators took precautions to protect engines and machinery from the abrasive particles. Aircraft rerouting became extensive as the ash plume expanded. Flights between Asia and North America that normally transited Alaskan airspace were diverted south, adding fuel costs and travel time. Cargo carriers faced difficult decisions about whether to delay shipments or accept the longer routes, and passenger airlines dealt with cascading schedule disruptions. The Volcanic Ash Advisory Center worked continuously to provide updated forecasts of plume movement, but the inherent uncertainties in atmospheric modeling meant that margins of safety had to be generous. No airline could risk an encounter with volcanic ash, regardless of the economic costs of avoidance. By the morning of March 29th, sensors indicated that the eruption intensity was beginning to decrease. The seismic tremor amplitude declined slightly, and observations suggested that the ash plume was not reaching quite the same altitudes as during the previous evening. This waning did not mean the eruption was over, as Pavlov's typical pattern involved pulses of activity that could sustain for days or weeks, with periods of higher and lower intensity. However, the peak appeared to have passed, and the most vigorous phase of magma discharge was transitioning to a more moderate but still significant level of activity. The volcano was not finished speaking, but it had delivered its loudest statement, and now the communities affected could begin to assess the immediate impacts while remaining vigilant for whatever might come next in the days ahead. Living in the shadow, the eruption persisted through early April, though never again reaching the intensity of those critical hours on March 28th. Pavlov settled into a pattern of sustained but moderate activity, emitting ash plumes that typically reached 15 to 20,000 feet and producing intermittent explosions that lit the night sky with orange incandescence. The volcano had entered what volcanologists call a sustained eruptive phase, where magma continued to reach the surface at a rate sufficient to maintain ongoing activity, but not high enough to produce the dramatic paroxysms of the peak period. For the communities downwind, this meant weeks of living with uncertainty and adapting daily routines to accommodate the persistent threat of ashfall. Cold Bay residents developed strategies for coping with the ongoing eruption. Ashfall occurred sporadically depending on wind direction and eruption intensity, sometimes heavy enough to require clearing from roofs and walkways, other times merely a light dusting. The town organized volunteer crews to check on elderly residents and ensure that those with respiratory conditions had adequate supplies of masks and medications. The local school remained open but modified outdoor activities, keeping children inside when ash concentrations in the air exceeded safe thresholds. Life continued, but with constant awareness of the mountain's mood and readiness to adjust as conditions changed. The economic impacts extended beyond the immediate area. Commercial fishing operations based out of Cold Bay and nearby communities faced decisions about whether to continue operations during periods of heavy ashfall. Ash contamination of catch could affect marketability, and the abrasive particles posed risks to boat engines and equipment. Some vessels chose to remain in port during the worst periods, accepting the lost fishing time as preferable to risking damage or operating in hazardous conditions. For communities where fishing represents the primary economic activity, these disruptions translated directly into reduced income and financial stress for families already operating on narrow margins. Aviation disruptions proved to be the most far-reaching consequence of Pavlov's eruption. The Volcanic Ash Advisory Center in Anchorage maintained continuous monitoring, issuing updates every 6 hours or more frequently when conditions warranted. Airlines developed sophisticated protocols for ash avoidance, using satellite data, pilot reports, and atmospheric modeling to chart safe routes. The costs of these diversions accumulated into millions of dollars across the weeks of sustained activity, a reminder that volcanic eruptions in remote areas can have global economic ramifications. Cargo shipments faced delays, passenger travel plans required modification, and insurance companies calculated risks and liabilities associated with volcanic hazards. Scientists at the Alaska Volcano Observatory maintained their vigil throughout the sustained phase, analyzing each piece of data for clues about how long the eruption might continue and whether another surge in intensity could occur. The seismic record showed that tremor persisted at moderate levels, indicating continuous magma movement, but not the dramatic escalation that would signal an impending paroxysm. Gas measurements revealed sustained emissions of sulfur dioxide, confirming that fresh magma continued to diga as it reached shallow levels. Satellite thermal monitoring detected persistent heat anomalies at the summit, consistent with ongoing lava effusion and explosive activity. All evidence suggested that the magma reservoir feeding the eruption still contained sufficient melt to sustain activity for an indeterminate period. The psychological toll of prolonged volcanic unrest affected different people in different ways. Some residents found the eruption fascinating, a reminder of the dynamic planet they inhabited and an opportunity to witness geological processes that normally operated on timescales beyond human perception. Others experienced anxiety from the constant uncertainty, the inability to know when normal life would resume, and concern about potential escalation. Children asked questions about safety that parents had to answer honestly while providing reassurance, a delicate balance between acknowledging real hazards and avoiding unnecessary fear. Community cohesion strengthened as neighbors supported one another through the shared experience, but the strain of sustained emergency preparedness gradually wore on everyone. Traditional knowledge held by the Aleut population of the region provided perspective that complemented scientific monitoring. Elders spoke of previous eruptions within living memory, describing patterns they had observed and outcomes that had resulted. While these accounts could not predict specific future behavior, they offered context about what communities had endured before and survived. The integration of this traditional ecological knowledge with modern volcanology represented a synthesis of understanding that benefited both scientists seeking to interpret data and communities seeking to make informed decisions about daily life. By mid-April, the eruption began showing signs of genuine decline. The seismic tremor amplitude decreased more substantially, and the continuous nature of the tremor gave way to more episodic activity. Ash plumes became less frequent and generally did not exceed 10,000 feet. Thermal monitoring revealed decreasing heat output from the summit crater, suggesting that the rate of magma reaching the surface had diminished significantly. These indicators pointed toward the eruption entering a waning phase, though scientists cautioned that renewed vigor remained possible if additional magma ascended from depth or if the conduit system reopened after partial blockage. On April 21st, following several days of minimal activity, the Alaska Volcano Observatory downgraded Pavlov's aviation color code from orange back to yellow. The eruption had not ended definitively, but the level of activity no longer posed an imminent threat to aviation. This downgrade allowed a degree of relaxation in the intensive monitoring and aviation warnings, though vigilance continued. By early May, with no significant activity for more than a week, the status was further reduced to green, indicating a return to background levels. The eruption that had begun in late March, reaching its climax on March 28th and sustaining through early April, had concluded. Pavlov had spoken, and now it returned to silence, leaving communities to clean up ash, repair any damage, and reflect on the experience of living through another chapter in the volcano's restless history. When the ash finally stopped falling and Pavlov's plume dissipated into memory, the work of understanding what had occurred began in earnest. Scientists descended upon the volcano during the summer months of 2016, conducting field studies that would have been impossible during the eruption itself. They hiked across fresh lava flows, collected samples of newly deposited ash, and documented the changes that weeks of eruptive activity had wrought upon the landscape. Every piece of evidence gathered would contribute to a more complete picture of how Pavlov behaves and what drives its frequent awakenings. Knowledge essential for improving future eruption forecasts and hazard assessments. The lava flows from the 2016 eruption had traveled significant distances down the volcano's flanks, in some cases extending more than 2 miles from the summit crater. These flows were primarily andesitic in composition, consistent with previous eruptions, and displayed the characteristic features of relatively viscous lava, blocky surfaces, thick flow fronts, and levees that marked the channels through which the molten rock had streamed. Samples collected from different parts of the flows would undergo detailed laboratory analysis, revealing information about magma temperature, crystallization history, and the conditions under which the magma had ascended through the crust. Chemical fingerprinting would allow comparison with lavas from previous Pavlov eruptions, helping scientists understand whether the volcano taps a single long-lived magma reservoir or multiple sources at different depths. Ash deposits provided another crucial source of data. The distribution of ashfall extended hundreds of miles from the volcano, with the thickest accumulations naturally closest to the vent and progressively thinner layers farther downwind. Scientists created isopatch maps, contours of equal ash thickness, that revealed the total volume of material erupted and the pattern of atmospheric dispersal. By analyzing ash from different stages of the eruption, researchers could reconstruct how the explosivity evolved over time. Ash from the peak phase on March 28th consisted of extremely fine particles with fresh glassy surfaces, indicating violent fragmentation of magma. Later ash showed more variability, including fragments of older rock from the conduit walls, suggesting that the explosions were excavating material from the volcanic throat as magma flux decreased. The seismic record from the eruption became the subject of intensive study. Every earthquake, every tremor episode, every explosion signal was analyzed to understand the subsurface processes that generated them. Machine learning algorithms were applied to classify different types of seismic events automatically, revealing patterns that human analysts might miss when examining thousands of hours of continuous data. The analysis showed that the transition from discrete earthquakes to sustained tremor occurred approximately 12 hours before the first surface explosions, a timing that could inform future eruption forecasting. The tremor itself displayed harmonic characteristics, regular oscillations that suggested resonance within magma-filled conduits, providing insights into the geometry of the plumbing system beneath the volcano. Gas emissions data offered clues about the magma's journey from depth. Sulfur dioxide measurements from satellites showed that emissions increased dramatically during the peak eruptive phase, reaching levels typical of moderate-sized volcanic eruptions. The ratio of different gas species, particularly sulfur dioxide to carbon dioxide, can indicate the depth from which magma ascended, because different gases become depleted at different pressure thresholds during ascent. The data suggested that the magma involved in the 2016 eruption had risen from depths of at least 10 miles, degassing progressively, as pressure decreased with the final explosive degassing occurring in the uppermost few hundred meters of the conduit. The eruption added approximately 40 million cubic meters of new volcanic material to Pavlov's edifice, a volume equivalent to a cube nearly 1,000 feet on each side. This may seem substantial, but in geological terms it represented a relatively modest eruption, classified as VA3 on the Volcanic Explosivity Index, a scale that ranges from 0 to 8. For comparison, the 1980 Mount St. Helens eruption was VA5, ejecting more than 100 times the volume of material that Pavlov produced in 2016. Yet the impacts of Pavlov's eruption were still significant for the region, demonstrating that eruption size does not solely determine consequences. Location, duration, and ash cloud altitude all factor into the hazard equation. Aviation impacts had been substantial despite the eruption's moderate size. Analysis by the International Civil Aviation Organization estimated that approximately 500 flights were affected by ash avoidance procedures during the 3-week period of sustained activity, with diversions adding over 10,000 hours of additional flight time and consuming roughly $15 million in extra fuel costs. These figures highlighted the vulnerability of modern air transportation to volcanic hazards and reinforced the importance of robust monitoring and communication systems. The 2016 Pavlov eruption served as a test of protocols developed after previous volcanic disruptions, and while the response was generally successful in preventing any aircraft encounters with ash, the economic costs demonstrated the need for continued investment in volcano monitoring infrastructure. For Cold Bay and the surrounding communities, recovery was measured not just in cleaning up ash, but in processing the experience and preparing for the inevitable next time. Community meetings brought residents together to discuss what had worked well during the eruption response and what could be improved. Emergency coordinators reviewed communication protocols, noting where information flow had been effective and where gaps existed. The experience became incorporated into local preparedness planning, and schools updated their emergency procedures based on lessons learned. The residents understood that they had not witnessed Pavlov's last eruption, nor even necessarily its largest within their lifetimes, and that the volcano's quiescence was temporary rather than permanent. The scientific community published papers in peer-reviewed journals documenting various aspects of the 2016 eruption, adding to the body of knowledge about Alaskan volcanism and subduction zone magmatism more broadly. Each eruption provides a natural experiment, an opportunity to test hypotheses and refine models of volcanic behavior. The data from Pavlov joined datasets from other volcanoes worldwide, contributing to efforts to understand the common principles that govern how volcanoes work despite their individual peculiarities. This cumulative knowledge serves the practical goal of improving eruption forecasting and hazard assessment, translating scientific understanding into tools that protect lives and livelihoods in volcanic regions across the globe. The 2016 eruption of Pavlov reinforced a fundamental truth about volcanology. That effective monitoring saves lives and reduces economic losses. But maintaining that monitoring infrastructure in remote and harsh environments presents formidable challenges. The Alaska Volcano Observatory operates as a partnership between the United States Geological Survey, the University of Alaska Fairbanks Geophysical Institute, and the Alaska Division of Geological and Geophysical Surveys. This collaborative model pools expertise and resources to maintain surveillance over more than 130 volcanoes across Alaska and the Aleutian Islands, a geographic expanse larger than many countries and characterized by some of the most unforgiving terrain and weather conditions on Earth. The monitoring network around Pavlov consists of multiple instrument types, each providing different but complementary information about the volcano state. Seismometers remain the backbone of the system, detecting ground vibrations that reveal magma movement, rock fracturing, and explosive activity. These instruments must withstand extreme cold, high winds, and the corrosive effects of volcanic gases while transmitting data reliably across vast distances where conventional communication infrastructure does not exist. Solar panels and wind generators provide power during summer months, but winter darkness and ice accumulation can compromise energy supply, requiring backup battery systems sized to sustain operations for weeks without recharging. GPS stations measure ground deformation with millimeter precision, detecting the subtle inflation that occurs as magma accumulates beneath a volcano. The technology relies on signals from satellites orbiting 12,000 miles above Earth, processed through sophisticated algorithms that account for atmospheric effects, tidal forces, and plate tectonics to isolate the deformation signal from Pavlov itself. These stations transmit their data via satellite links to processing centers where automated analysis flags any significant changes for immediate human review. The system provides near real-time awareness of deformation trends that would have been undetectable a generation ago, transforming the ability to anticipate eruptions. Satellite remote sensing has revolutionized volcano monitoring by providing observations that do not require instruments on the volcano itself. Thermal infrared sensors detect heat anomalies that indicate shallow magma or active lava flows, while other instruments measure sulfur dioxide emissions by analyzing how gases absorb specific wavelengths of sunlight. Synthetic aperture radar can measure ground deformation across entire volcanic edifices with spatial resolutions of meters and vertical precision of centimeters, revealing patterns of inflation and deflation that help scientists understand how magma reservoirs fill and drain. These space-based assets orbit beyond the reach of volcanic hazards, providing continuous observations regardless of weather conditions that might obscure visible light imagery. The data streams from all these instruments flow into the Alaska Volcano Observatory Operations Center, where duty scientists monitor displays that update continuously. Automated alert systems flag anomalies for immediate attention, but human judgment remains essential for interpreting whether changes indicate normal background variation or the beginning of unrest that could lead to eruption. This interpretive challenge is complicated by the fact that each volcano has its own personality, its own patterns of behavior that may differ substantially from neighbors. What constitutes a clear warning sign at one volcano might be routine at another, and experience monitoring specific volcanoes over many years builds the institutional knowledge necessary for accurate interpretation. Communication of volcanic hazard information to stakeholders represents the culminating purpose of all monitoring efforts. The Alaska Volcano Observatory issues regular updates on volcanic activity levels using standardized alert systems designed for clarity and consistency. Aviation color codes inform pilots and air traffic controllers about threats to aircraft, while volcano alert levels communicate hazards to emergency managers and the general public. These systems operate internationally through the International Civil Aviation Organization and the World Organization of Volcano Observatories, ensuring that volcanic hazard information is disseminated quickly and in formats that users can understand and act upon. The success of these communication protocols during the 2016 Pavlov eruption, with no aircraft encounters with ash, despite hundreds of flights affected, validated the effectiveness of this systematic approach. Yet monitoring infrastructure faces perpetual challenges of funding and maintenance. Instruments in remote locations require periodic site visits by technicians, who must access areas reachable only by helicopter or small aircraft, weather permitting and often at substantial cost. Components fail due to extreme environmental conditions, wildlife interactions, or simply the accumulated wear of operating continuously in hostile settings. Budget constraints force difficult decisions about which volcanoes receive the most comprehensive monitoring and which must be observed primarily through satellite-based methods that, while powerful, cannot provide the same immediacy and resolution as ground-based instruments. Every volcanic crisis highlights the value of monitoring investment, but sustaining that investment during periods when volcanoes are quiet requires ongoing advocacy and recognition that preparedness costs far less than response to unmonitored eruptions. The global context matters because volcanic hazards respect no borders. Ash from Alaskan eruptions can affect air routes across the Pacific and into Asian airspace. Lessons learned monitoring Pavlov contribute to improved monitoring of volcanoes in Indonesia, Japan, the Andes, and other volcanic regions where populations face similar or greater risks. International collaborations share data, methodologies, and expertise, recognizing that volcanic hazards represent a common challenge to humanity. The volcanic ash advisory centers that coordinate aviation responses to eruptions operate as a global network, with centers in Anchorage, Tokyo, London, Buenos Aires, Darwin, Montreal, Toulouse, and Washington, each responsible for regions but sharing information freely to ensure comprehensive coverage. Looking forward, emerging technologies promise to enhance monitoring capabilities further. Drone-based systems can survey volcanoes at close range without exposing personnel to hazards, collecting gas samples, thermal imagery, and visual documentation. Fiber optic cables deployed on volcanic slopes act as distributed seismometers and temperature sensors, providing unprecedented spatial resolution of subsurface activity. Machine learning algorithms trained on decades of volcanic data can potentially identify subtle patterns that presage eruptions earlier than traditional analysis methods. These advances build upon the foundation of seismic, geodetic, and satellite monitoring that proved its worth during events like the 2016 Pavlov eruption, incrementally improving the capability to forecast volcanic behavior and protect communities living in the shadow of restless mountains. The eternal dialogue Pavlov remains active in the years following the 2016 eruption, a reminder that volcanic quiescence is merely an intermission rather than a conclusion. The volcano erupted again in 2024, producing ash plumes and lava flows in patterns familiar to those who had witnessed previous events. Yet each eruption carries its own variations, its own unique expression of the forces churning beneath the surface. The communities that live within sight of the mountain have learned to accept this reality, understanding that their home sits at the boundary between stability and transformation, where the solid earth reveals its fluid nature and the timescales of geology intersect with the rhythms of human life. The relationship between humanity and volcanoes has always been complex, characterized by simultaneous attraction and wariness. Volcanic soils are among the most fertile on Earth, enriched by minerals from the planet's interior, and civilizations have consistently chosen to settle near volcanoes despite the hazards they pose. The slopes of Mount Vesuvius supported thriving towns in Roman times just as they do today. The flanks of Mount Fuji have been cultivated for centuries. The island of Java, one of the most volcanically active regions on the planet, supports a population density exceeding 1,000 people per square mile in some areas. Humans are drawn to volcanoes by the very processes that make them dangerous, accepting risk in exchange for the benefits that volcanic landscapes provide. In Alaska, the calculus differs because population density remains low and most volcanoes stand far from permanent settlements. Yet the principles remain the same. Cold Bay exists where it does partly because of geography shaped by volcanic and tectonic forces, a harbor and landscape that made it strategically valuable during World War II and economically viable for fishing communities afterward. The residents accept the proximity to Pavlov not because they are indifferent to the hazards, but because they have developed the knowledge and infrastructure to live with those hazards at acceptable levels of risk. They monitor forecasts, maintain emergency supplies, and adjust their activities when the volcano stirs, creating a practical accommodation with a force that cannot be controlled or negotiated with in any conventional sense. The scientific understanding of volcanoes has advanced remarkably in recent decades, transforming them from objects of superstition and fear into subjects of rigorous study whose behavior can be anticipated with increasing accuracy. Yet, profound mysteries remain. The exact triggers that determine when accumulated magma will erupt, rather than solidify at depth, are not fully understood. The processes that control whether an eruption will be effusive or explosive, brief or prolonged, remain areas of active research. The potential for unanticipated behavior, for eruptions that deviate from historical patterns, means that volcano monitoring must combine statistical analysis of past behavior with real-time assessment of current conditions, acknowledging both what is known and what remains uncertain. Pavlov persistence serves as a microcosm of the broader reality that Earth remains a dynamic planet where continents drift, mountains rise, and the interior heat that has driven these processes since the planet's formation continues unabated. The energy released during the 2016 eruption, impressive as it seemed to observers, represented a tiny fraction of the heat flux escaping from Earth's interior through all volcanic systems globally. The magma that fed Pavlov's eruption originated from processes operating across millions of years as oceanic crust formed, traveled across the Pacific, and descended into the mantle at a subduction zone. The eruption was not an isolated event but a single note in a symphony that has played since the Aleutian arc began forming tens of millions of years ago and will continue until plate tectonics fundamentally reorganizes this region of the globe. For the people of Cold Bay and Nelson Lagoon, for the pilots who navigate Alaskan airspace, for the scientists who monitor the instruments arrayed around Pavlov, the volcano represents both a hazard to be managed and a window into the planet's workings. Each eruption provides data that refines understanding, improves forecasting capability, and ultimately enhances the capacity to live safely in volcanic regions. The 2016 eruption harmed no one, disrupted economic activity but caused no catastrophic losses, and contributed valuable information to the global effort to understand volcanic processes. This outcome reflects both the relatively moderate nature of the eruption and the effectiveness of monitoring and communication systems that have been developed through decades of effort and investment. The future will bring more eruptions from Pavlov, perhaps within months or years, perhaps not for decades, but certainly within the lifetimes of many who witnessed the 2016 event. Some future eruptions may be smaller, brief episodes that cause minimal disruption. Others could exceed the 2016 eruption in intensity, duration, or impacts, testing the resilience of communities and the adequacy of preparedness measures. The volcano operates on its own schedule, driven by processes that human activity does not influence. What can be influenced is the level of preparation, the quality of monitoring, the effectiveness of communication, and the resilience of communities that choose to remain in volcanic landscapes. Standing at Cold Bay on a clear day, looking across the water to where Pavlov rises against the sky, one sees a landscape of stark beauty, a mountain perfectly shaped by its own construction, layer upon layer of erupted material built over millennia. Smoke or steam often rises from the summit, a visible reminder that the volcano breathes. The scene appears timeless and, in a sense it is, representing forces and processes that predate human civilization and will continue, long after our current societies have transformed into whatever follows. Yet it is also intensely temporal, a moment in ongoing change where any day could bring the next awakening. The dialogue between Earth and those who dwell upon it continues at Pavlov as it does at volcanoes worldwide. The planet speaks in tremors and emissions, in inflation and heat. Humanity listens through instruments and interprets through science, responding with preparations and adaptations. Neither side of this dialogue understands the other completely, but the conversation proceeds nonetheless, an exchange between geological time and human time, between forces that built continents and communities that persist in their shadows, between the permanence of stone and the persistence of those who choose to call volcanic landscapes home.